Okay, so starting with page 1.
Okay.
Okay, x sine x, need for derivative rule for sine, but also product rule needed. Okay, number 2, let f be the function given by f of x, on which of the following intervals is the function increasing. So we gotta go through first derivative test. Find f prime. Set f prime equal to 0. Critical points, sine y. Okay, so my critical points are 10 and negative 10. Has values in each region. Into the factored form of my f prime. 10 minus negative 11 is positive, 10 plus negative 11 is negative, positive negative is negative. Decreasing 0, 10 minus 0, 10 plus 0, that's positive. 11, 10 minus 11, 10 plus 11, negative. Okay, so increasing will be in the middle interval here from negative 10 to 10. Page 2. Secant tangent, so you recall our derivative rule for tangent. Secant u tangent u times u prime. So if this is one of the rules that you memorized and are able to put onto the beginning of your multiple choice test, the 6 main derivative rules, you can take the antiderivative going backwards, right? Secant tangent will take you back to tangent. I'm sorry. Secant is secant tangent. Tangent is secant squared. The secant is secant tangent, so integral of secant tangent will bring you back to secant. Okay. 4 is pretty easy. Just have to find the derivative and evaluate the derivative at 1. You have to remember a rule here. Natural log of u is u prime over u. 7x becomes 7. 3 equals 0. Natural log of x becomes 1 over x.
Mr. Can you explain, like where a limit would not exist? Because I got number 5 wrong when I did it. But like, I guess I understand like why now, but is there any like other time where a limit would not exist?
Yeah, so limit would not exist if the graph is disconnected like this.
Okay,
It would also not exist if there's an asymptote like this,
okay,
or if it's just an endpoint and nothing is occurring on the other side.
gotcha. Yeah, thank you.
So which of the following statements is false? We know that approaching 4, right? If I pick points on either side of 4 and I draw an arrow towards 4, I can see that my arrows are not headed in the right towards the same y value. So therefore, the limit as x approaches 4 would not exist. It would be false. A particle moves along the x-axis, velocity is given. What's total distance? So first, I want to make sure that if there even a change in direction in the first 3 seconds. So let me set my velocity function up.
Would it matter if there's a change in direction because it's a total distance?
Yeah, it would matter because if there's change in direction, then the integral is going to give us a negative value. We have to take the absolute value of each region.
Okay.
So, but this is a little bit easier because we're going to see that from 0 to 3, there's no change in direction. So otherwise, we have to look at each region and make sure every region is positive. There's only change direction at 0 and 6, so we're safe. 0 to 3, we can take the integral. That'll give us the change and that'll give us our displacement, which is enough for total distance. 27 minus 9. Okay, we got a function within the function. Prefer not to fool this out with that high of an exponent. We're just going to go through chain rule. So outside derivative, parentheses to the fifth power becomes 5 parentheses to the fourth. And then inside derivative, 3x squared minus negative sine x. Tank contains 50 liters of oil. This is the starting point. Oil is being poured or pumped into the tank at a rate of R of T. R of T is here. This is liters per hour. Where R of T is measured in liters per hour. T is measured in hours. Selected values of R of T are given. Use right Riemann sum. What's the approximation of the number of liters that are in the tank at time t equals 15 hours? So we know that we use Riemann sums to help us find how much oil has been added, but then we need to add it to what was there to begin with to be able to figure out how much oil there is at the end time. So total equals initial plus displacement. You know, there's 50 liters to begin with at 4 hours. And then we can figure out how much oil has been added in that time period, 11-hour time period. Width times height. So width comes from that 3, the height comes from the second row. 3 times 6.2, 5 times 5.9, 3 times 5.6. Add that together, use your calculator, or in this case, we got to just add it by hand. Number 9. Let k be the be the function defined, where value of k is f continuous. So anytime I see a continuous or continuity problem, I'm always thinking, okay, can I just step through my continuity conditions and just see how things play out? Okay, so first is, does a point exist at 2? I know that at 2, it's just some y value. Okay. It's still unresolved, so I'll keep going. The limit. I know that limit is for extended connected parts of graph, not for the order pair. So the graph is sitting in this first piecewise, because x doesn't equal to 2 means everywhere except 2. So that all the connected parts are here. So I just find the limit of my graph, not for my point. Okay, plug 2 in, I get 5 times 0 over 0. So 0 over 0. Can do L'Hopital's rule, but in this case, I think it's easier and faster if I just reduced and reevaluated. So my limit is 5. So the third condition just goes back and says, okay, look at the first two that you've accumulated, and are they in agreement? Well, we can force them to be in agreement if k is equal to 5. Number 10. What's the area of the region in the first quadrant? E to the x over 2 and the line x equals 2. Well, we know that e to the x looks like this. So e to the x over 2 is just going to be a transformed version of this, but very much looks the same. First quadrant. Area. So area is just top minus bottom. Integral from 0 to 2. Okay, have to go through a little bit of u substitution to get that 1/2 x taken care of. Take my substitutions. Pull the 2 out in front. Take the antiderivative. We know e to the u is an easy rule. This is just itself. So e to the u becomes e to the u. Normally I would do plus c, but we have bounds involved. So I'm going to bring back my original variable. And then work in my original bounds. 2 over 2 is 1. Careful. E to the 0 is also 1. So I get 2e to the first power minus 2. Okay, number 11. The function be defined by f of x equals square root of absolute value of x minus 2, which the following statement is true. Whenever you have absolute value, you know it's going to be a sharp turn here. And then, but that square root is going to give it a little bit of a curve. So we know the graph is nicely continuous, but it's not going to be differentiable, meaning that there's a sharp turn there. Okay, number 12, use substitution. Giving us a hint that u is root x, but you want that root x to be up here. And we're hoping that I want to go through our u substitution, that root x will go away on its own, and we're left with e to the u. Power roll. Okay, make your substitutions. The root x cancels out. 2 gets pulled out in front. But in this case, we're asked to find out what the bounds will be in terms of u. So I have to convert the 1 and 4 in terms of u. Plug the 1 and 4 in for x, so 1 in for root x. Root 1, u is still 1. Plug 4 in for root x. Root 4 is 2. So 1 to 2. Okay, function is defined. You got piecewise function. What's the value of the area from 1 to 5? So we have to basically do depth integral for both regions. 1 up to 3 under one graph, and from 3 to 5 under a different graph. Okay, power rule for both, and then plug in the respective bounds. So 25 minus 9 is 16. 16 over 2 is 8. 8 minus 5 is 3. 3 plus 3 is 6. So I got a 4. I got a 6. Add those together, I get 4 plus 6 is 10. Okay, let me build f of g of x first. Insert the g into the x of the f function. Find this derivative, and then I can plug in the 3. So chain rule here. Okay, outside derivative. Times inside derivative, so the derivative of this is another chain rule here. 2. And another nested 3 inside. Oh wait, hold on. I think my key may be showing something a little bit off here. I'm going to plug in 3 here. Excuse me. I'm going to build each of the functions here. So h prime is just the derivative of this. Second theorem, which just takes us to f of x. H double prime is just f prime. So we know h of 6 is going to be some negative value. H prime of 6 is f of 6, which is 0. H double prime of 6 is f prime of 6. F prime of 6 is the slope. The slope of 6 is positive, like 1. So A. Now lowest value, 0, followed by a positive value. The particle moves along the x-axis. So the following is particles at rest. Particles at rest is when velocity is equal to 0. could go through product rule here, but I'm just going to pull this out. First. Remember, A and B are just unknown constants, so we'll leave it treated like constants. T squared becomes 2t, AT becomes A, BT becomes B, AB goes 0. Set velocity equal to 0. Solve for T. Remember, A and B are just, it's complicated, but A is just some unknown constant, so we'll just have to solve for T. Move A and B over. Divide both sides by 2. Okay. Figure shows graph of f. F is the integral from 2 to x of g of t, which the following could be the graph of g of x. So let's just figure out what that relationship is. So basically, this is the derivative graph of g. So what could be the g graph? Well, if this is the derivative graph, let's imagine this is a slope of 2. Then I want a graph that is just showing a y value of 2, right? I'm sorry, this is the original graph, my bad, original graph. So g is the derivative graph. So if this is slope of 2, we want a derivative graph to show our y value represents the slope value. So if this y-intercept is 2, then it's going to hold that same slope all the way through. Looks like a messy limit problem, but first thing we always do is plug in our x value, in this case our h value. Natural log of 4 plus 0 is natural log of 4 minus natural log of 4 is 0. 0 over 0 is indeterminate form. We know we can go through L'Hopital's rule. U prime over u for natural log. Natural log of 4 is 0. H goes to 1. Evaluate the limit. H in for 0, we get 1/4. Okay, f is defined as x over x plus 2. What points x, y on the graph has a property that is tangent has a slope of 1/2. So we can just set the derivative equal to 1/2 and try to go backwards, work backwards, solve for x. So to find the derivative, I have to go through quotient rule. So I'm gonna set my derivative equal to my slope. Cross multiply, solve for x. Square root of both sides. I got two numbers. X plus 2 equals 2, x plus 2 equals -2. I get 0 and 4, 0 and -4. So I know my x values. Just have to find my y values at these 2 points. So insert 0 back into the original function. 0 over 0 plus 2 is 0. -4 for x, -4 for -4 plus 2. This -4 over -2 is 2. Those are my two order pairs. This is find the derivative of an inverse at a point. Got an inverse function. Find the value of g prime 1. I like to go through my table here. I know 1 is the y value of my f function, so I can go try to figure out what that x value is. So I can solve this out here. Actually, I can test this out, right? If I plug in 0 for x, 0 plus 1 is 1, 1 cubed is 1, so x equals 0. So if I can find f prime of 0, I can get to my g prime of 1. So let's find f prime of x first. Chain rule. Get 6. For f prime 0, so g prime 1 must be the reciprocal 1/6. Okay, horizontal asymptote. Take a limit. And the limit's going to give us 5 for e. If I take the limit as x approaches infinity, I get x squared. I'm going to match up. 20 over 4 is 5. One and 2. What's the absolute minimum? So we set f prime equal to 0. Solve for x. Okay, so quotient rule is needed. F prime g minus f g prime all over g squared. We can set the numerator equal to 0. We get e test values at either of my critical point. Increase followed by decrease. I know my relative max is at e, but it's asking for the value. So I got to plug e back into the function to get that y value. I'm gonna stop at a little bit short of page 8, but I'll pick up this section in